Okay, hello everyone. Welcome to another episode of Science and Technology Q&A for kids and others. Sorry, we're starting a little later than usual. I was giving a talk to an interesting conference, and so I've been answering other questions for quite a while here. All right, let's take a look at what we've got for today. Let's see. A question here from Jack. How common is atomic oxygen in the universe? Okay, so what is the universe mostly made of? Well, mostly the universe is quotes empty space. In quantum mechanics and in our theories of physics, quotes empty space isn't really actually empty at all, but in terms of kind of the things we can normally identify, like molecules and atoms and so on, it is considered empty. There's about, altogether in the universe, it's about 1 hydrogen atom per cubic meter is the typical content of the universe. By far the most common of the chemical elements is hydrogen. Well, helium is about 25% of the abundance of hydrogen in the universe. And as you go to heavier and heavier elements, the abundance gets ever smaller. How do the elements, how does that abundance arise? Well, what happened is at the beginning of the universe, in the Big Bang, the universe was extremely hot, and there were kind of all possible particles were produced. As the universe cooled down, most particles, all the unstable particles just decayed away. What got left over were things like protons and neutrons, electrons. And what eventually happened was that those protons and neutrons and things were bouncing around at very high temperatures, running around at very high speeds. And kind of when the music stopped, so to speak, as the universe expanded and things cooled down, when the music stopped, most protons hadn't found a partner. Most protons were just sort of free floating and had maybe, those free floating electrons turned into hydrogen atoms. Sometimes they'd found a partner, which was a neutron or other protons or whatever, and those turn into heavier elements. So the chance to have a heavier element gets ever smaller, because at the time when kind of the music stopped, when the universe expanded to the point where it was cold enough that these things would not be typically running into each other, there was a question of sort of how many protons had accumulated together. And so you see this, if you look at the different chemical elements, you'll see this distribution of abundances in the universe left over from the Big Bang. Now, different chemical elements also get made in stars and get made in supernovas, which are explosions of stars. Those can make heavier and heavier elements by processes of nuclear fusion, where you take nuclei of different elements and ram them together, and they stick, and that makes a heavier element. But so the typical situation is that you will get you'll mostly have these light elements like hydrogen, helium, lithium, beryllium, and so on. The early elements in the periodic table are by far the most common in the universe. And okay, so the question was about atomic oxygen. I don't know what the actual abundance of oxygen is. If you look at the abundances of different elements in the universe, it's not actually a uniform distribution. It's not just the bigger the element, the less abundant it is. It's a little bit more complicated than that. Some of that is the result of nuclear fusion in stars, and some of it is the result of detailed properties of nuclei and the fact that certain kinds of nuclei are more stable than others. Certain nuclei, when protons had ran together, and maybe there was some cluster of 20 protons and a few neutrons, that would break apart into particular nuclei, and there are particular nuclei that are more stable, and so they're more commonly produced. But then the next question is, when you have just an atomic nucleus, let's say an oxygen nucleus hanging around with its 8 protons and maybe 8 neutrons or something in it, is that right for oxygen? I think that's right. When you have that, there's a question of, will it make a molecule? Like the most common form of oxygen, for example, in our atmosphere is O2, a pair of oxygen atoms bound together by sharing electrons. That's the most common form. Actually, in the upper atmosphere, there's also ozone, which is O3, which is a slightly unstable form of oxygen where there are 3 oxygen atoms all bound together in the same way by sharing electrons. But so the question of, will you get oxygen that hasn't bound together into O2 to make an oxygen molecule like that? It's sort of a question of how often does a single oxygen atom find another oxygen atom to pair up with? If the oxygen is sufficiently sparse, then it just won't find another oxygen atom to pair up with to make molecular oxygen. Now, if you look in space and you ask the question, you just look out in the universe and you say, what kind of molecules are there out there? Is there oxygen? Is there water, H2O? Are there various kinds of hydrocarbons and so on? The answer is that it at first looks a bit surprising because there are actually quite big molecules that have been made in space, so to speak. And that can happen, perhaps it happens on little grains of dust that some atom will land, another atom will land, and it will get start sharing electrons with some existing atom, and the whole thing will make a molecule that will then sort of float away from that grain of dust. Maybe it can happen just in empty space with atoms running into each other. It's not so clear, but the answer is that you get these comparatively complicated molecules. And when they were first observed, people said, oh my gosh, there are all these interstellar molecules. They're actually molecules that are not that different from molecules that exist in biological organisms in some cases. And it's like, isn't that remarkable that it's possible to make those things just in space? And well, it's just because these molecules are just things that happen when you just throw atoms together, they'll tend to form these molecules. The kind of distribution of different kinds of molecules that are formed in space is really different from the distribution that are formed in, for example, biological systems, but still some of the molecules can be comparatively complicated. Let's see. There's a question here from Ide. If temperature and pressure both come from gas molecules bouncing around with certain momentum, why are the two different? What's the difference between the two? Okay, that is, I think, he says, famous last words, a comparatively easy question to answer. It's always very dangerous here. Whenever I think a question is easy, I haven't seen some horrible trap somewhere something which has sort of seemed obvious to me because I've known it for 50 years, but isn't actually that obvious. But let me give this one a try. So what is temperature? Temperature is the average kinetic energy of molecules, for example. So kinetic energy is the energy associated with motion, with molecules moving around, and it's the formula is it's a half mv squared, where m is the mass and v is the velocity. That's the kinetic energy associated with a molecule, with anything actually, with any object just running around at a certain speed. So temperature is associated with the kinetic energy of molecules. It's the energy of motion of the molecules. Pressure is associated with transfer of momentum by molecules. So pressure is, you say the pressure is determined by, if you put walls around the gas, how much will the gas push outwards on the walls? How does the gas push outwards on the walls? Well, the answer is these molecules are all bouncing around, and occasionally a molecule will hit the wall and it'll bounce off. And when the molecule hits the wall, it's going in a certain direction, it will give momentum to that. Its momentum will be used to push the wall in a certain direction, and then the molecule will bounce off the wall and its momentum will have been, let's say, reversed by the presence of the wall. So in other words, the molecule is transferring its momentum to the wall. So what's happening is that pressure is a measurement of the amount of momentum that could be transferred by the gas across that boundary that corresponds to the wall. And so, again, temperature is just the energy with which all these things are running around, which for a given mass of molecule translates into the speed that the average speed that the molecules are moving at. There'll always be a distribution of speeds. It's actually a thing called the Maxwell-Boltzmann distribution. The speeds are exponentially distributed, but there is an average speed that the molecules are moving at, and that average speed characterizes the temperature of the gas. That average speed also determines the pressure of the gas, because that pressure, well, it also is related to the pressure of the gas, because that average speed also determines, for a single molecule hitting the wall of the container, that determines how much momentum the molecule can transfer. But there's another factor. The other factor which determines the momentum, the transfer, the pressure, is the density of molecules in the gas. So the temperature is just the energy of individual molecules, which determines the speed of molecules. It doesn't say anything about how many molecules there are in the gas. But the pressure depends also on the number density of molecules. So it depends also on how many molecules are there per unit volume in the gas. And so, in fact, the formula, let's see, I think the formula for the pressure of a gas is it's proportional to, I think it's 1/3 nc square bar. So it's n is the number density, that is the number of molecules per cubic meter, let's say, in the gas, and c square bar is the mean square velocity of mean square speed of the molecules. So temperature is proportional to the let's see, the temperature is, well, kT, half kT, is, let's see, temperature is proportional to the square of the speed of the molecules, and the pressure is proportional to the number density times the square of the speed of the molecules. So the reason that pressure and temperature can vary independently is that the temperature is determining one factor in the pressure, that is the part that comes from the speed of the molecules, but there's another factor, which is the number density of molecules. So in kind of high school physics, you might learn the gas laws that say pressure times volume equals a constant times temperature. And if we think a little bit more about what I've just been saying, we could actually derive those gas laws, because we're saying that the volume of the gas, if we keep a fixed number of molecules and we change the volume, the number density of the molecules is going to change. So if we halve the volume, the number density of molecules is going to increase by a factor of 2, because they're the same number of molecules in half the volume. So that means that if the volume is halved, that means the number density increases by a factor of 2. And that means if we take the pressure, which is proportional to number density, times the volume, and we change the volume by a factor of 2, that pressure times volume will keep constant, because assuming it's what's called adiabatic, which means that we don't change the energy, we don't change the temperature of the gas. Well, actually, that's a tricky. I always say that these are that's actually so-called isothermal, keeping the same temperature. But that's the reason that pressure times volume keeping the same temperature is a constant, is because the pressure is proportional to the number density, which increases as the volume decreases, the number density will increase. And that's kind of how one can understand the gas laws that determine the sort of overall pressure and volume and temperature of a gas. By the way, the thing to say, the standard formula is PV equals RT or whatever, where R is a constant. If that formula was the whole story of a gas, you wouldn't have liquids, you wouldn't have refrigeration, you wouldn't have a bunch of other things. That formula is just an approximation. That formula is an approximation that works when the gas is sufficiently dilute. It assumes that basically gas molecules just bounce off each other. They don't really interact at all. But in real gases, the gas molecules, if you kind of squash the molecules down far enough, eventually they're interacting so much that the gas will condense into a liquid and the molecules will all kind of stick together. In a gas, the molecules are just sort of separately bouncing around. But as you get closer to the point where the gas has been either compressed or the temperature has been reduced to the point where it becomes a liquid, the molecules are more and more, the interactions between molecules become more and more important. And those interactions produce a correction to the gas law. And that correction to the gas law is what leads to, well, the fact that you can get a liquid, and also the fact that you can do refrigeration by letting gases expand And as the gas expands, it's kind of losing energy because some of its energy is being spent in the interactions between the molecules, and that energy that's being kind of absorbed by interactions between the molecules is removed from the temperature of the gas, which is how the temperature of the gas manages to go down. And that's essentially the mechanism by which one can get, for example, liquid gases. You know, you can make liquid nitrogen or liquid oxygen. You can make air liquid, so to speak. That's also the thing that if you wonder about, like, you know, how cold can it get on the Earth? One thing is that it takes some, you know, the minimum temperature is certainly going to be above the temperature at which air becomes a liquid, because it sort of takes more effort to make the air liquid. And so that isn't something that will happen just by virtue of the way that climate works in the atmosphere. Let's see. So Ben is asking, how should I educate children, like my experience growing up, in order to give them the best potential for any STEM field? Well, let's see. I mean, I've got a few meta things to say. You know, I myself just got interested in science when I was pretty young and just started learning all kinds of stuff about it. And for me, with my particular turn of mind, I was always like, is there a question I want to know the answer to? Maybe I can find out the answer in a book, or maybe I have to go figure out the answer somehow. But I think that the first sort of meta thing is to realize that, you know, just you can ask a question, and it's like, you can, you know, the answer might be known, the answer might not be known. There are questions where the answer isn't known, and those are okay to ask too. And it's kind of just an issue of just like exploring as much as possible what and trying to understand what's known and what's not known. You know, I think it's difficult when people are like teaching science in an organized way, as opposed to perhaps my way of trying to do it, which one might not characterize as systematic and organized, so to speak, is if you imagine the stream of questions, and we see that here in these live streams that people ask, they range from questions where the answer is knowable by sort of high school level physics, let's say, to questions where, for example, I know the answer is not known, or questions where, yes, I've thought about that, I know the kind of the very edge of research in that area, and maybe I've even figured out something about it myself. But the sort of questions when they're asked by kids, for example, and we see that in these live streams, they range across all these different levels of difficulty of questions. And I think it's an important thing to kind of imagine that one can explore all of those. That's a really useful thing. Also, just, I mean, a general point about education is that there are lots of facts to know in the world, and, you know, knowing more facts is super useful to understand what's going on, even if in the end, what's the most powerful thing is to understand principles and methods and so on. Those have to be hung on a kind of framework of facts, and it's really worth learning the facts, so to speak, to be able to sort of go from those to sort of abstract to principles and methods and so on. Now, when it comes to more technical levels of sort of learning STEM kinds of things, I have to make the pitch to learn kind of computational language, and to learn, you know, there's this giant stack of technology we've been building for the past 40 years or so, that now has turned into things like Wolfram language and so on, that are a way of taking kind of thinking about the world and thinking about things computationally. And one of the great things about computational language is that if you can formulate your questions in computational language, then you, together with the computer, have the chance to be able to answer even questions that nobody has been able to answer before. And sometimes the thing that's really worth learning is how to formulate those questions in computational terms, in computational language, so that you can get the computer to help you answer those questions. And then often the answers you'll get are answers that literally nobody has ever seen before. So you can discover new things, and that's kind of a thrill to be able to do. So I think those are things that I might say are things I consider to be useful. I would say that my efforts here in these live streams to provide kind of, well, I would say that when one learns science, there are ways to learn science that are pretty boring, really, where you're just learning things which are on a particular path that never runs into any difficulties, where you're just saying there's a certain set of things where we know them well and they all fit together very nicely, and it's kind of a straightforward story. There's another way to learn science, which has to do with kind of knowing what's interesting and kind of looking at the interesting things. And sometimes there will be sort of places very close to the path of interesting things where, or even on the path of interesting things, where we just don't know. That science is simply not known yet. And I think that there's a certain tendency when one teaches science in kind of a school setting or something like that, to go only on the path where it's all very safe and where everything is known. But I think that it is much more exciting to understand the path of science that includes things where one has to say, well, I'm sorry, we just don't know that yet. And not to be afraid of those kinds of things, even though it doesn't work so well. You know, if you have the multiple choice test or something that says, you know, is the, what is the size of an electron? Is it 0, 10 to the minus 93 meters, 10 to the minus 20 meters or whatever? Well, we just don't know the answer. So there's no kind of multiple choice, you know, checkbox that can be filled out yet. Nobody knows that yet. There's a question here from Reed. If I were in my 20s, young 20s, and just graduated from college, which field would I go into? AI and machine learning, aerospace engineering, blockchains and crypto, and so on. You know, it's a very personality dependent thing. You can go into there always, at any given time, there's a field that's kind of in rapid growth. And it lasts maybe 5 or 10 years that rapid growth happens. If you want to kind of run with the pack and really try and, you know, do things around this pack of people who are all rushing in the same direction, then you should go into these fields that are popular at any given time. If, on the other hand, you want to kind of be more relaxed and just, you say, I'm going to do something original, but it doesn't have to be something where there's a whole pack of people going in that same direction, then you can go into a much sleepier field and go and do something great and innovative in that field. You won't have any competitors. You'll have to explain to people why what you've done is important, but it's a much sort of calmer life in some sense. Right now, the areas, I would say my own feeling is, of the ones you mentioned, you know, AI and machine learning, I kind of think that has been something where there's sort of a new methodology that came in maybe 10 years ago now that has unlocked a bunch of kinds of computational approaches. I think we're seeing the end of the period of rapid growth for that particular area. We're not seeing the end of the applications of that area. There will be applications forever, and there will be an increasing number of increasingly useful applications probably, but it is the sort of the early kind of pseudo basic science side of it. I think that's pretty well worked through at this point, and we're really into the kind of the sort of engineering applications type phase right now, and it's going to be a slower growth story. Aerospace engineering, you know, when I was a kid, I was interested in space, and there was the 1960s, and space was a big thing. And I actually got interested in physics first by being interested in things like spacecraft, and I was thinking, how would you design a spacecraft to do this or that? I'm really glad I didn't decide to spend my life doing spacecraft, because the world has just not been in a place where spacecraft have been sort of a happening thing until very recently. You know, one of the things which will, I think, be a determiner of what happens in the sort of the new space period is, it's clear that it will become ever easier to sort of put things in space. And then the real question is, so what's the point? What's that going to be good for? You know, there was a time in the 1960s, for example, 50s and 60s, when exploring the oceans was like, this is the absolutely the thing, you know, submarines and all that kind of thing. It's going to be great. There are going to be cities under the ocean and so on. That didn't happen. And, you know, there's going to be, we're going to be able to do mining in the ocean. We're going to be able to do this, that, or the other in the, et cetera, in the ocean. That didn't happen. Now, in space, what will the moon colony be for? It's not clear yet, at least not to me. Once we but things may very well emerge. Really good things, really interesting things may emerge. And, whether it's satellite imagery, which emerged in the early period of space, whether it's communications, those kinds of things, those are things we now know are going to be things in space, but we don't know what else will emerge. We don't know what else will turn out to be important. I mean, there was a time when people said that growing perfect crystals in the zero gravity conditions of in orbit and things would be really important. That hasn't panned out yet, but we don't really know yet. So I think the jury is still out in terms of what will be kind of the evolution of space, so to speak, in spacecraft and so on in what comes. Now, you said aerospace in general. That's another interesting question. Will it be the case that there are dramatic innovations, whether it's hydrogen-powered planes, whether it's electric planes, whether it's supersonic planes? Will those be things that become a significant part of the landscape or not? There was a time when I was younger when the Concorde was supersonic plane was thought to be, this is the future. This is really, everybody's going to be taking supersonic flights. I'm happy to say I took one flight on the Concorde. It was fun. I had some particular time when I was in London and I needed to be in New York shortly thereafter, and I thought, what the heck, I will splurge and take a flight on the Concorde. And it was kind of fun to the physics of it was interesting to me. It flew high enough, 55,000 feet maybe, that the sky, which is normally blue from scattering of sunlight in the atmosphere, it's black at those heights even during the day. So that was a fun feature. The other fun feature is, I've studied sort of supersonic motion through fluids and so on, and it's kind of fun to actually feel what it's like to sort of break the sound barrier and so on. And the way it was in the Concorde, they had this big thing at the front of the cabin where they had a speed meter, because after all, you were paying for the fact that you were going really fast, so they had to show how fast you were going. But Mach 1 is defined to be the speed of sound, and so there was you could kind of see the typical plane might fly at Mach 0.9 or something, Mach 0.85, 0.9, that kind of thing. The reason one doesn't want to fly reason it's hard to fly faster than the speed of sound is that there are shock waves that develop around a plane. When the plane is going faster than the speed of sound, essentially all of the sound waves that are produced by the plane moving through the air all build up and form this shock front. It's kind of like if you ride a bicycle through a puddle, you'll see this kind of wall of water that comes from behind that's sort of in this cone or this behind where your bicycle wheel goes. And that's kind of a shock which comes from all these little water waves that were produced by the effect of your bicycle. They all kind of pile up at that particular place. And it's the same thing with sound waves. And that piling up of sound waves produces a variety of different ways to see it. It produces a discontinuity in pressure in the air and so on. And it's something which produces lots of stress on the structure of the plane. Actually, there's another phenomenon, which is right when you get towards the sound barrier, when you get towards the speed of sound, there is an instability that starts happening in the flow of air over the wings of a plane. So normally the air is, when the wing slices through the air goes above the wing, below the wing, and the wing is kind of slicing through the air. And the air flows kind of smoothly over the top of the wing or the bottom of the wing. But right near the speed of sound, a strange phenomenon happens that causes there to be an instability in the air, and the air kind of forms this kind of wave that sort of oscillates on the wing. And in fact, the place where the air kind of separates away from the wing, kind of that front oscillates around, and that leads to this kind of this leads to this instability. And that's what, when people tried in the 1950s to first have planes that flew faster than the speed of sound, the planes kept on falling apart or otherwise failing because of this, the kind of all this instability that happened from the flow of air over wings right around around Mach 1. Well, it was kind of interesting, my one trip on the Concorde, to kind of feel that instability. You could kind of feel the thing kind of juddering around, and you could also see that it was just below the speed of sound. It was pushing, and it was and its engines were running, so to speak, and it took a little bit of more effort to get over the speed of sound, and then after it got through speed of sound, it could accelerate fairly rapidly, and that was just sort of an interesting thing to feel the physics, so to speak, in that case. But the question of whether it will turn out to be the case that things like supersonic planes, electric planes, things like this become popular, that's as much a societal and complicated engineering question as anything else. For example, drones, which, for example, particularly quadcopter drones, where the idea of those had existed for 50 years. It just hadn't been possible to implement them because the particular technologies to do with the flight controllers, that was the control system, that it wasn't possible to have the right kind of computers. It wasn't possible to have the battery density to be able to run the electric motors in such a way that the batteries weren't too heavy to lift, all those kinds of things. Those various engineering sort of curves had to align to the point where it was possible to do something. And so now drones exist. Will supersonic planes exist again? Not clear. Possibly yes, possibly it'll be another 50 years. Will people care about it when they exist? Back in the day when I would go I would have to drive in a car a long distance. It's like, I can't do that. That's way too boring. I can't spend 3 hours driving. That's like horrifying. Or what am I going to do for 3 hours? Well, now, of course, then there were cell phones. And now, I don't mind going on a long drive because I've got phone calls I want to make and things like that. And I'm kind of happily doing things. Similarly, going on a longer plane trip, it's like, well, I just get out my computer and I start doing what I would normally do, and I'm connected to the internet, and it's all good. I'm just like, I've got a nicer view out of the window. And it doesn't really matter to me so much whether I'm going at a supersonic speed and able to cross the Atlantic in 2 hours instead of 5 or something. So these things that are determined by sort of human effects of how much do people really care about getting to their destination that much faster? Maybe there's a use case where that's really important. Maybe it's important for something, but I'm not sure that people will care as much as they once, for example, this phenomenon of, I don't mind driving a long distance because I can do something like be on a phone call, is just wasn't something I might have expected. It's just another piece of technology that sort of converged. And so I don't know what the future of aerospace will be from that point of view. It seems like an exciting area right now where a combination of sort of the push for clean energy versus the fact that there's sort of commercialization of space and so on, these seem like things that are driving a lot of interesting possibilities there. What will turn out to be societally useful or cared about is a little bit harder for me to predict. Now, you asked about blockchains and crypto. That's definitely a very energetic area. That's an area that I think is pretty interesting because it's kind of an area where it's forcing a rethinking of a lot of things that we imagine. Now, is it, in a sense, a blockchain? So, the idea of blockchain, the earliest being Bitcoin, the blockchain is sort of two different ideas all merged together. One idea is the idea that you can have this kind of ledger, this thing that says what happened. You say, this event happened, this thing happened. Let's put that in our ledger, and let's arrange that ledger to be in this chain of blocks where we guarantee that every block we add guarantees that all the previous blocks are correct. And I could explain, maybe I did once before, I can explain in great detail how that works. But essentially the idea is you're adding more and more blocks, you're adding more and more things that you can put on this blockchain. And when you add a block, you're guaranteeing that everything in the past is accurate. So let's say you're trying to record who owns that house. and you say, I'm going to put that on the blockchain. And it's there, and everybody can, and people can see it on the blockchain, but you guarantee, as you add more things to the blockchain, you guarantee nobody can change that thing that was earlier on the blockchain. You can't sort of take out that brick and have the rest of the structure remain intact. So that's kind of the important idea of blockchain is this kind of ledger that builds up. And the other important idea is that it's a distributed ledger in the sense that there are many copies of it. Like for Bitcoin, there might be 10,000 copies of the ledger around the world, and those things are always kept consistent. Again, long story exactly how that works, but basically the point is that there are these many copies, maybe 10,000, maybe more copies of that ledger, and so it's not possible for somebody to say, I'm just going to change it, I'm going to adjust it. It's something where it's a sort of permanent record in the world. That's one thing. One application of that is to money, because if you want to know, if you say, well, I've got this coin and I want to say, I own this number of coins, and I've got the information that I own this number of coins is on the blockchain. And then I give one of these coins to somebody else, and that transaction is on the blockchain. So now that person has a coin and I have one less coin and so on. And you're recording all of this information on the blockchain. That's kind of the idea there. Now, what gets more elaborate is that you can have not just transactions in which you just, somebody pays somebody with one coin, but you can actually have programs that run, for example, on the blockchain that are specifying that, I don't know, you have some lottery, let's say, where people put money in, and then the program running on the blockchain will just randomly pick one of those people to pay out all the money to, let's say. That turns into probably a yet more interesting idea, which is the idea of computational contracts. The idea that you can have, normally when you have a legal contract, it's written down in words and so on. It says, one person, if A gives B $100, then B will mow their lawn or something. And that's what the contract says, and it's in words. But you can have a computational contract, which is a program that says, if this computer receives this money, then this camera will check that the lawn got mown, and if it didn't, then this will happen, and that will happen, and so on. And it's all something defined computationally. And that's really a thing that has just starting these days to be a big thing, that sort of turning the way that the world is specified into these computational contracts that have to be written in kind of a computational language. Now that overlaps with the whole world of blockchain, but it isn't quite the same thing. You can have computational contracts not using blockchain. You can have blockchain not using sophisticated computational contracts. But the combination of those things is kind of a redefinition of how a lot of kinds of business processes and a lot of kinds of things in the world actually work. So, I mean, I would have to say that I think there's great sort of very diverse collection of different things that are happening around the blockchain and crypto world. It is a strange world because, if you look at these different fields, if you look at AI and machine learning, you look at aerospace engineering, look at blockchains, you ask what kinds of people with what kinds of skills are going into these fields? Well, AI and machine learning, it's a bunch of people going through computer science departments, a bunch of people with physics backgrounds, because a lot of the mathematical analysis is very physics-based. And there's also quite a lot of kind of engineering, software engineering type, almost hackery that goes on around that kind of thing. So that's one type of person. When it comes to aerospace engineering, you really have to be an engineer to do that. Well, there are strategy kinds of things that can be done otherwise, but you really have to be an engineer thinking about things in an engineering kind of way and imagining, how would we make this wing curl in this way and this thing work in that way? And if you're just a programmer, for example, it's a little bit less of a thing where you can really make a contribution. You really have to know the engineering to make a contribution there. In the world of blockchain and crypto, it's interesting because it's a very general field. And if you just have some strategic idea and you know about finance, or you know about physics, or you know about mathematics, or you know about computer science, you know about program verification, all these different fields have relevance to the picture of what's happening in blockchain and crypto. It's also the case that the sort of the educational backgrounds of people in that area, very diverse. If you look at people in aerospace, they will have studied aerospace engineering. it's very unlikely that you'll have somebody there. Maybe they've studied physics, but they won't have been somebody who did, you know, art history and then decided to build supersonic planes. That's not a common path. Whereas in blockchain and crypto, there's just tremendously diverse educational and, in fact, cultural and other backgrounds that people have coming into this blockchain area. And it creates a rather interesting kind of melting pot kind of field where there are lots of opportunities. There's also a fair amount of nonsense there. And that's, you know, that's a place where if you're in a field where there's a fair amount of technical knowledge that's needed to really enter the field, it tends to be a much narrower story in terms of there's great stuff, there's not so great stuff, but it's all reasonably sensible. Whereas if there's a field where there isn't much of a barrier to entry, and it's kind of just like, if you choose to get into the field, you can do it, there can be total nonsense and really wonderful stuff. And they both kind of populating that field. But I would say that it's a field where there's a lot of opportunity for blockchains, and crypto is a field where there's just sort of a lot of opportunity for thinking about all kinds of different things. Now, will you be successful in that field? Sometimes, because there's this, it's not as narrow a kind of definition of what success looks like. Some of these things depend on societal factors. Some of them depend on kind of predicting kind of how people will react to things and so on. It's a field where it's sometimes a little bit harder to know what's going to come out based on what you put in. But I think it's a very energetic and active field that's also very intellectually interesting, because it mixes all sorts of things about kind of computational contracts, which have to do with kind of AI-ish sort of computational language questions, have to do with sort of the how you think about law and computational terms, things like this, together with things like verifying how that the blockchain can never cause one to double spend a coin or something. That's a whole story of kind of program verification, together with all sorts of things about how different kinds of business processes work. It's really an area where there's a lot of diverse kinds of things to be thought about, a little bit like what happened with early social media, social networks, and so on, where again, it was something where, you know, the raw technology was a piece of it, but there were a lot of other factors that came in. I would say blockchain is a broader area than that, but it has some of the same kind of character to it. Let's see. The question from Aaron: is there a closest packing for Spikeys? Spikeys are these things, I don't know, I've probably got one behind me there. Let's see, I actually have a paper one here. This was the model Spikey that was made by my older daughter years ago, that we were creating Spikey kits. And this was the test Spikey that was made for one of those Spikey kits, which I happen to have on the shelf here. But anyway, this is a Spikey. And the question that was being asked is there a way of packing these things together? And the answer is they don't pack as a tiling of all space, but you can pack them. You can make various kinds of linear packings of them. You have to have, boy, I should know this. I even wrote a long piece about it. You have to have you can't fill space just with Spikeys. You have to have another piece as well to be able to just sort of fill up space with them. You're asking what's the largest and smallest Spikey. I think there are some very small ones that exist in strange kinds of crystals, crystalline materials, some kinds of lanthanum manganese something compounds that form little quasi-crystals that are that kind of shape. So that's something which will be maybe 100 millionth of a meter across, something like that. The largest Spikey I've ever seen, well, I've seen pictures of pretty big Spikeys. I saw one somebody made that was about a few times the height of a person. So that's a fairly large Spikey. I'm not sure I've seen, somehow I think that was there's a strange event that I've never been to called Burning Man. That's a kind of a strange sort of festival in the desert where all sorts of terrible things happen. But I believe people have made sort of spiky-like ornaments for that are pretty big. But I don't think, I'm guessing on the order of, I don't know, 20, 30 feet across. So that's probably the largest I've seen. Let's see. I should wrap up fairly soon here. Let's see. Questions about from Reed about, will we see AGI this century? So what is AGI? AGI is artificial general intelligence. What does that mean? Well, when I started knowing about artificial intelligence kinds of things, probably now, 50 years ago now, people would say, as soon as computers can do X, Y, or Z, then they'll be intelligent. They'll be just like humans. So what were X, Y, and Z? There were things like, as soon as computers can do math, like humans do it. As soon as computers can drive cars, like humans can do it. As soon as computers can recognize images, like humans do it, then they'll be intelligent. Well, each of these kinds of things has been able to be done by computers. But people say, well, but I can see inside. I can see how the computer does math. And it's not really intelligent. It's just using algorithms and programs to do math. But, well, that was the test, and computers passed that. Now, another test is, can you have a conversation with a computer and not know that you're talking to a computer rather than to a person? That's often called the Turing test for intelligence, invented by Alan Turing in 1950. This idea of if you're talking to a thing and you wonder, is it a computer, is it a person? Maybe you can't tell the difference. I have to say, just yesterday, somebody sent me something which was a computer-generated conversation. And it was a computer that had learnt from a bunch of examples, billions of words of actual conversation, of actual text on the web and elsewhere. And it kind of learnt the pattern of different kinds of conversation and so on. And its goal was to simulate a real conversation. And so this person had taught it based on a bunch of text, perhaps some transcripts of these live streams, had taught it to talk like me. And so I was really curious, what would it be like? What would this machine-generated, AI-generated thing that's like me be like? It was awful, just awful. It was, on an individual sentence by individual sentence basis, the sentences were grammatical, which is good. I hope my sentences are usually grammatical. But it was, it couldn't sort of maintain a thought. It couldn't maintain a thread of thought. It was just sort of throwing out random sentences, far away from the kinds of things that we humans end up talking about. So that's a place where people say, look, we haven't reached artificial general intelligence because we can't have like a conversation with a computer like that. But one of the things that's tricky is to say, you have to kind of contextualize what kind of a conversation would you like to have? If you're trying to, book a plane ticket or something, well, that's a conversation with a very specific objective, and that's not out of range for what can be done today. In fact, there are systems that do a pretty good job of that kind of thing. If you want to have a free-ranging, let's talk about anything you feel like talking about, well, what are you going to talk to the computer about? You can say, how do you feel today, to the computer? Well, how does a computer feel today? Hard to know. That's a difficult question to answer. Computers don't have the same kinds of experience of the world that we do. If you give a computer if you have the computer walking around with you and kind of experiencing the world like you experience it, well, then perhaps you can have a conversation in which the computer is like, well, my owner, so long as computers have owners, which they will for a while, my owner thinks this, that, and the other. It's kind of, I've been walking around with them, and this is their experience, and now I can, as a computer, talk about their experience like it's my own type thing. And so, this question of when will we get to the point where you can have that's really the last frontier, I think, is this kind of, when can we have a conversation with the computer like we can with a person? And I think, in limited cases, that's not far away. The real question for an AI is, what does the AI want to do? Us humans have our own strange motivations for why we want to do this or that, which come from our own personal history, the history of our whole culture, the set of values we have, all kinds of things like this. Those are the overarching things that determine what we choose to do. And this question about how do you set goals, that's not something where we can say, well, let's automate setting goals. What would be the automatic goals that are set? Well, you'd have to say, what's the goal of the goals, so to speak? You don't know, there's no sort of ultimate mathematically defined goal that you should have. Maybe one possibility is to say, don't go extinct, because if you go extinct, you're not going to have any goals at all. But even that, you might argue about whether that's the right goal for the AI is the don't go extinct goal. Maybe it's not the right goal. Maybe if the humans want to be in charge, it's not the right goal to have the AIs be absolutely dead set on not going extinct. So, it's a thing where in the end, the goals have to be, the goals are not precisely defined. The goals are not abstractly defined. The goals are just defined by what we humans choose to make the goals. And so that's something that no AGI, so to speak, is going to determine its own goals, because it doesn't make sense to think about that. Things do what they do, like things in the world, things in, the weather does what it does. And you could say, well, it looks as if it's having goals to do this or that, but actually it just does what it does. And we also operate according to physical laws and just do what we do, but we have at least this idea that we have definite goals and so on. And that's just not something that you can translate to, it just doesn't mean anything to translate that to this other thing that's this AI. You have to give it the goals, so to speak. It can't be the ultimate source of those goals. So I think in that sense, it's now, sometimes the goals can be far removed from what the AI is actually doing. I mean, a famous example of that is, the AIs that determine sort of the ordering of content in social media or in search engines and so on. The question is, what is the goal of that AI? Well, the goal might be maximize revenue by making the content be something where people will engage with it as much as possible, click on the ads as much as possible, whatever else. That might be the ultimate goal of the AI as defined by the company that's running the AI. But what that actually means in terms of what the actual content that comes out in this stream is, well, that's a complicated story. And for example, the AI has discovered, I mean, this is a fact, that the AI has discovered that the more outrageous the content is, the more likely people are to click on it and read it and engage with it. So that means the AI, even though that wasn't the original goal on the part of sort of the humans who were setting the AI up to maximize ad revenue, that still is the consequence. Is it turns out humans have this feature that they're more likely to engage with outrageous content. So there's more outrageous content that's generated there. And so that's kind of a feature of the AI where I suppose in some sense it's operating in a general intelligence kind of way, doing those kinds of things given its overall goal. So I would expect that what we'll see in terms of AI is we'll see more and more kind of symbiosis between us humans and AI. When augmented reality becomes common, which will finally happen after many years of it not happening, we'll regularly be seeing sort of annotations to our everyday life generated by AI. So right now, if in sometime in the future, my glasses will probably have something which is producing some augmented reality thing, and it's reminding me about all kinds of stuff. Oh, you should say this. Oh, that connects with this thing that you've thought about before. Those are ways that we will kind of share our experience with AIs. And meanwhile, the AI that is connected with me will be learning from the things that I'm saying and doing. And eventually it'll say, you really like doing this or that thing. I've noticed that when you do this or that thing, then whatever happens. And so I think there'll be sort of increasing symbiosis between us and the AIs that we're connected to. And I think eventually the line will somewhat blur between what is kind of the pure human activity and what is the AI helping the human. That's already happened to some extent. I mean, whenever we sort of follow the auto suggestions when we're typing things into a computer, whenever we follow a GPS in a car or something, we're kind of letting the AI determine some of what's happening, and we're kind of operating in this way that's in collaboration with the AI. Let's see. well, we should probably wrap soon here. Maybe one more question. All right, we'll try one more here. One more. This was about from memes asking, what's the deal with superfluids? Any useful purposes? Okay, what is a superfluid? So normally, if you have some water, for example, and you put your hand in the water and you swirl the water around, you'll make this kind of vortex. The water will be going around in a circle, but it won't take long before the water will sort of calm down, and the motion that you put into the water will just sort of decay away, and the water will be still again. What causes that kind of stopping of motion is the phenomenon of viscosity. Viscosity is kind of a damping of motion. It's kind of like an analog of friction between solids. Kind of the analog of that inside a fluid is viscosity. And some fluids have higher viscosity than others. If you have syrup, for example, it can have very high viscosity. It doesn't like to flow very much. Whereas if you have other fluids, in syrup, treacle in British English, you'd have, if you start off some motion, will very quickly decay away. In water, the viscosity is lower, and so it will take longer for the motion to die away. Okay, so a question is, are there any fluids that have zero viscosity? Can you have a liquid that has zero viscosity, where you start this vortex going and it will just keep going for days, weeks, years? The answer is yes, there are. They're so-called superfluids. And what is a superfluid? So the most common example of a superfluid is liquid helium-4. Helium-4, when I say helium-4, I mean it's helium where there are 2 protons and 2 neutrons in the nucleus of that helium atom. So what happens is when you cool helium-4 below a certain temperature around 4 degrees above absolute zero, I think, it becomes a superfluid. So what happens? When you cool something down, the molecules, we talked about this actually earlier in this live stream, the temperature corresponds to the motion, the speed at which molecules are running around. As you cool something down, the molecules get slower and slower and slower, but most of the time, there's still, even when you get to absolute zero of temperature, where the molecules shouldn't be moving around at all, there are quantum effects that cause there to be some motion in the molecules. But there are cases in which there is enough, essentially, interaction between molecules that even that 0 point energy at absolute zero gets essentially removed. And this happens, superfluids are essentially the analog of lasers in fluids. So in a laser, you've got all these photons, and the photons are all collected together in such a way that photons like to do the same thing as each other. So if you get photons set up in the right way, they'll all like to go at the same frequency in the same direction, the same phase, and that's why this laser is sort of a coherent piece of light. The photons, they're so-called boson particles, and the bosons have this feature that they all like to be in the same state. And that can happen with helium-4 atoms as well, that they can all want to be in the same state. So that these helium-4 atoms sort of collectively do things. They all, vote together, so to speak, to do something. And that means that when you start up motion in helium-4, and when it's a superfluid, that motion, all the atoms just keep doing what their friends were doing, so to speak. And that means that you kind of keep this motion going. There's no possibility of having that little bit of friction, that little bit of viscosity that will slow the motion down. And so that means that in a superfluid, you will have motion that will just keep going, no viscosity. And so that means that you can have these circulations in superfluids that just keep flowing forever. And they've been made to do that for years, actually. If you keep things cold enough, they'll just keep flowing, keep flowing. That's the way that works. Now, the question was, are there useful purposes for superfluids? And I'm wondering about the answer to that question. because I am not immediately thinking of one. Superfluidity was discovered nearly 100 years ago, maybe even a little bit more than 100 years ago now. Oh gosh, what are the uses for superfluids? There are some ways of doing refrigeration that to very, very low temperatures that use, actually they use mostly versions of helium that don't, that aren't superfluidic. Gosh, I don't know. It's a wonderful phenomenon. I mean, superconductivity, which is the ability of electrons to sort of flow without friction, to just keep flowing in a wire. Superconductivity is useful as a way to be able to have larger amounts of current to make stronger magnets used in most, in particle accelerators, some MRI machines, things like that, to be able to have stronger magnets. Unfortunately, the problem with superconductivity and superfluidity is that both of them require very low temperatures, and that's just a big nuisance to deal with. Let's see, I'm wondering whether people have tried to make quantum computers out of superfluids, and I don't think that they have, although I think it's something you could imagine doing. I'm blanking on this. I'm not thinking of any applications of superfluids. Let me think. Can I even imagine applications of superfluids? See, it's a big nuisance that they have to be within a few degrees of absolute zero. So that makes it kind of hard to have them exist. I am not immediately coming up with any application at all, which is, so that's a thing for the future, so to speak, for physics, is, a lot of phenomena, like when liquid crystals were discovered, back in the 1800s, I don't think anybody knew that they would have an application. And of course, they were used for a long time in displays, even still used in displays for computers and so on. So I don't know in the case of superfluids. Good question. I have to think about that one. All right, we should probably wrap up here. Thanks a lot for those interesting questions. And next week, we should be back to our regularly scheduled time. Thanks for joining us here.